For the first few minutes, I am going to talk about the importance of light, how is that it has affected our daily lives, and then I will talk about the evolution of the different models of light. I will try to answer the question as to what light is. The photograph on the left is that of a setting sun, and the photograph on the right is a light beam getting guided through an optical fiber, and that is my name, and I used to be at IIT Delhi, and that is my email address. The study of light has fascinated mankind ever since he could see. Here we see a sadhu worshipping the light from the sun. In fact, in 2015 was proclaimed as the International Year of Light. On 20th December 2013, the United Nations General Assembly proclaimed 2015 as the International Year of Light and Light-Based Technologies, and it was abbreviated as IYL 2015. And throughout the world, there were numerous events that were organized, and including many events in India. In proclaiming this, the United Nations has recognized that light plays a vital role in our daily lives, that light plays an extremely important role in our daily lives. It has revolutionized medical diagnosis and treatment, from eye surgery to the removal of a tumor. It has revolutionized international communications via fiber optics, and it has created extremely important devices for the industry and also defense. Why has this study of light become so very important? In the past, people have been wanting to know what light really is, but the study of light has, during the last 50 years, assumed tremendous importance, because of which all major universities in the world have a separate program in the general area of optics and photonics. Why has this happened? And that the answer is that Theodore Myman, who was an American scientist, he fabricated the first laser in May 1960. On the left is a photograph of Theodore Myman, and on the right is the laser that he fabricated. And as you can see, the light coming out from this laser is very directional, and it has only very small spread of wavelength. It is said to be almost monochromatic. What is the main difference between the light that comes out of a bulb and the light that comes out of the laser? The photograph on the left is the light from an ordinary light bulb, which spreads out in all directions. On the other hand, the photograph on the right, which shows a laser beam launched from a telescope, is very directional. In this particular case, it crossed the sky and created an artificial star at a height of 90 kilometers in the high Earth's mesosphere. One can see that the spreading of the light beam is extremely small. This is one of the very important characteristics of a laser light, and because it is directional, it can be focused by an ordinary lens into a very small area. In this diagram, we have shown a very directional light beam to fall on an ordinary lens, and it gets focused to a tiny region whose diameter is about 2 lambda f by a. So, where lambda is the wavelength of the light, f is the focal length of the lens, and a 2a represents the diameter of the incident beam. Thus, if a collimated plane wave of diameter 2a of the type that is incident from a laser, if that beam is incident on a lens of focal length f, then the wave emerging from the lens will get focused to a spot of radius about lambda f by a, which would be of the order of 1 micron. 1 micron is 1 micrometer, that is 1 millionth of a meter. And just for comparison, I thought I will tell you that the diameter of the human hair is about 100 microns. Now, what do you mean by the wavelength of light? You see, light, as I will discuss later, is an electromagnetic wave, and starting from gamma rays which are emitted in an atom bomb to X-rays which are used to diagnose human body, to ultraviolet rays, to infrared microwaves which you use in your microwave ovens, and the radio waves which you receive on your radio and TV sets. They are all electromagnetic waves. The only difference is the frequency of the gamma rays is extremely large, and the frequency of the radio waves is comparatively much less than that of gamma rays. They all travel with an identical velocity in vacuum, and this velocity is exactly 299,792.458 kilometers per second. All wavelengths, all frequencies travel with an identical velocity in free space. We will usually assume that this value is approximately 300,000 kilometers per second, which is equal to 300 million meters per second. That is the velocity of light in free space, and as we all know, because of this finite velocity, it takes about 8.5 minutes for light to reach from the surface of the sun to the earth. The visible region of the electromagnetic spectrum, which occupies a very small region of the entire spectrum, starts from the blue region, which has the smallest wavelength of about 0.4 micron, and the green region has a wavelength of about 0.5 micron. The yellow region has a wavelength of about 0.6 micron, and the red region has a wavelength of about 0.7 micron. So, that is the wavelength associated with the visible part of the electromagnetic spectrum. The corresponding frequency would be obtained by dividing the speed of light by the wavelength. So, one will get from the green region about 600 terahertz. 1 terahertz is about 10 to the power of 12 hertz. So, this frequency will be 6 into 10 to the power of 14 hertz. This frequency will be 5 into 10 to the power of 14 hertz. So, therefore, if we assume the yellow region of the spectrum, so the wavelength is about say 0.5 microns, the focal length of the lens is about 10 centimeter, and the diameter of the beam is, let us suppose, 2 centimeters, then simple calculation will show that lambda f by a is about 5 microns. So, that is the, so it gets focused to a distance of about 10 microns. And because of that, even a low power laser beam can produce very high intensities at the focal plane of the lens. Here we see a laser beam getting focused by an ordinary lens, and the electric fields at the focal point can be about 1,000,000,000 volts per meter, and the electric field is so large that that it can produce a spark in air. Similarly, if you have a focused laser beam, the laser beam is coming from here and it is getting focused by an ordinary lens, and the power of the beam, the intensity of the beam at the focal plane is so large, it can drill through concrete. This particular photograph is from an institute in India which is known as the Raja Ramanna Center for Advanced Technology in Indore. And therefore, one can appreciate the power of the laser beam, and in fact, because a laser beam is almost parallel, the lens of the eye will focus them down to a very small spot which can cause retinal burns. And because it produces an extremely high intensity here, it can also be used for treatment of retinal detachment. So, this is one of the very important application of the laser. So, if the intensity of a laser beam entering the eye is about 1 milliwatt per centimeter square, then the intensity at the retina will be about 100 watts per square centimeter. Thus, because the laser beam is extremely directional, it can be focused to a very narrow spot, and so therefore, whereas it is very safe to look at a 1000-watt bulb which is emitting light in all possible direction, but it is very unsafe to look at even a 2 milliwatt laser beam. So, one has to be very careful in handling a laser beam. It can burn your skin, it can burn the retina of the eye, and because it can produce such high intensities, it can also be used to weld the retina to the eye itself. So, it has tremendous applications in eye surgery and in other areas. I have just told you about the eye surgery, but there are many other areas in which the laser beam is extensively used. Here is a very beautiful experiment in which there is a red light beam corresponding to the frequency omega incident on a suitably oriented crystal, and the light that emerges from the crystal has double the frequency. So, that the red light incident at a particular angle generates the blue light. This area is usually referred to as the domain of nonlinear optics and has become extremely important area of research because of the advent of laser. Here is a laser beam coming out of a laser pointer. You must have seen laser pointers in your school and colleges. So, the green laser that comes out, in many of the laser pointers there is a red laser inside which falls on a suitably oriented crystal, and it generates twice the frequency. Here is a light beam which gets guided through an optical fiber, and there is a human hand holding the end of the fiber. Laser pulses propagating through millions of kilometers of optical fibers now connect us through the oceans. All major cities in India are also connected through optical fiber. Today, you can telephone your relative in the United States almost free of cost, and this revolution is possible because of the fiber optics and also because of the availability of very high speed lasers, that is lasers which can be modulated with extreme rapidity. And so therefore, the internet revolution that has occurred, the telephones becoming almost free through dialing any part of the world, that has become possible because of advances in the general area of optics and photonics, and this has happened because of the advent of laser. In fact, the 2014 Nobel Prize in Physics has been awarded to these three gentlemen for the invention of efficient blue light emitting diodes, LEDs, which has enabled bright and energy saving white light sources. And these LEDs are going to revolutionize the illumination technology throughout the world, particularly the developing world, because we can use the solar energy to illuminate such bulbs. And even in India, there is a major effort to have LED bulbs installed operated through solar energy in remote areas, in villages where there is no electricity. So, this is a revolution that has occurred. So, the future, I have tried to tell you a few experiments which show you the great tremendous importance and applications of light, and we feel that in generations to come it will be full of light, implying that light will find applications in most areas of working. And so therefore, study of light is of extreme importance, and as I mentioned earlier, most universities abroad have a separate department of optics and photonics, and intense research work in different areas of optics are going on throughout the world. So, in the remaining part of this lecture, I will try to tell you the various models describing what is light. Before that, I thought I should also tell you why 2015 was chosen as the International Year of Light, and that is because 1000 years back Alhazen wrote the first book on optics, and Alhazen was from Mesopotamia, which is now in Iraq, and he wrote a 7-volume treatise on optics, which was used by all scientists in Europe to do research in the general area of optics, to celebrate this. And on the photograph on the right shows the cover page of a translated edition of Alhazen's Optics. And to celebrate 1000 years of the first book on optics, the year 2015 was declared as the International Year of Light. Nobel Prize winner Abdus Salam said that Alhazen was one of the greatest physicists of all times. We have also been wanting to know what light is, the light that comes from the sun, what it contains. Sir Isaac Newton wrote the book on optics in 1687, which got published in the year 1687, and in that book he wrote, and I am quoting Newton, that are not the rays of light very small bodies emitted from shining substances. That is, he assumed that tiny particles are emitted from a body which is emitting light, and he said that because light was found to travel almost in straight lines. However, if we sit on the staircase of a shadow, we can still read a book. There is still some light which enters the shadow. That is not due to the phenomenon of diffraction, that is due to the phenomenon of scattering. scattering of light by air molecules, the nitrogen and oxygen that is present in air scatters the light beam into the shadow. What is scattering? You see, for example, I have tried to show you the orbit of a comet. A comet comes in, gets attracted by the force of the sun, by the attractive force of the sun, and its trajectory gets deflected. So, this deflection of the trajectory is known as scattering, which is, we can say that the comet undergoes scattering because interacting with the field created by the sun. So, similarly, the light also this undergoes what is known as Rayleigh scattering, which is inversely proportional to the fourth power of the wavelength. Smaller the wavelength, as we had seen earlier, the blue color, the blue region of the spectrum has a smaller wavelength. The smaller the wavelength, greater will be the Rayleigh scattering. So, higher the wavelength, smaller will be the Rayleigh scattering. And as we had told you earlier, that the blue region of the spectrum has a very small wavelength and the red region has a large wavelength. And so, therefore, the light from the sun scatters predominantly the blue component, and that is why the sky appears blue. So, once again, the sky is blue because the blue component of light gets predominantly Rayleigh scattered by the atmosphere. And the setting sun is red because the blue component of light gets predominantly Rayleigh scattered by the atmosphere. So, the white light that the light that we receive on our looking at the sun, the blue component is out. So, therefore, the sun appears predominantly red in color. If we are on the surface of the moon, as you all know, moon does not have any atmosphere or just very, very little atmosphere. So, the shadows are perfectly dark. You will not be able to read a book in your own shadow. If you stand in the sun and let us suppose the sun is on your back, and you can easily read a book in your own shadow, because as I told you, the light enters the shadow region because of scattering by the air molecules. But those air molecules are not present on the surface of the moon. And so, therefore, the shadows are completely dark and very sharp, and you will not be able to read a book in your own shadow if you are standing on the surface of the moon. So, here you see on the photograph that the sky is completely dark. This is on the surface of the moon, this is earth, and the sun is falling in this direction, and the shadows are very sharp and the shadows are very dark, which shows that light almost travels in a straight line. I thought I should mention that much before Newton, early in the 17th century, Pierre Gassendi and in 1637 René Descartes had put forward the corpuscular model of light. So, it seems Newton was aware of this, but in his book on optics he did not mention the works of these two gentlemen, and since his book became very popular, the corpuscular model of light is usually attributed to Newton, although 2-3 scientists before him had put forward the corpuscular model of light. So, therefore, we do this experiment. This diagram has been adapted from the famous Feynman lectures, that there is a gun which is emitting tiny bullets, and this is an arrangement of 2 holes. So, the bullets are emitted from the gun in all possible directions, and they hit the hole and arrive on this screen, and there is a detector on this screen. So, let us suppose only hole number 1 is open and hole number 2 is closed, then the arrival rate of the bullets is somewhat like what is given by P1, the arrival rate at the screen. If hole number 1 is closed and hole number 2 is open, then the maximum gets shifted, and you have an intensity distribution or arrival rate distribution which is given by P2. So, you have a detector which collects the bullets in a particular interval of time, let us suppose 1 hour, and then you repeat the measurement scanning the entire screen. However, if both holes are open, then the bullets either go through hole number 1 or through hole number 2, and so therefore, you obtain an intensity distribution which is given by P12, which is just the addition of the numbers P1 and plus P2, because these are tiny bullets which either pass through hole number 1 or hole number 2, and we say that there is no interference. Now, around the time of Newton, Christian Huygens, the Dutch astronomer, put forward the famous wave theory of light around 1650. So, the best way to understand the propagation of wave is to make a pointed needle vibrate on the surface of water, and the circular ripples appear to emanate from the center. There is a propagation of a disturbance. The water molecules do not travel, they just transfer the energy from one molecule to the other, and the disturbance spreads out horizontally in the outward direction. Each molecule then they are actually not strictly transverse waves, but for the sake of simplicity we assume that they are transverse waves, that is, the water molecules move in an up and down fashion. So, let us suppose it is moving up and down, and with a certain frequency, that is 10 times in a second or 20 times in a second, it moves up and down, and then the disturbance gets propagated in the outward direction. The distance between 2 points which are vibrating in the same phase is known as the wavelength. So, what is a wave? Another simple demonstration of the wave is through a string. Let us suppose I am holding one end of the string and you are holding another end of the string, and I make it oscillate in the x direction. Then I create what is known as an x polarized wave, and associated with an x polarized wave, the displacement is given by x as a function of z and time is equal to a cos k z minus omega t. If you ask a mathematician what is a wave, he will say that this equation represents a wave. So, let me tell you what I imply by that, the displacement of the string is given by x of z of t. A represents the amplitude and the cosine k z minus omega t. This equation describes a wave. So, let us suppose at time t equal to 0, the displacement will be x of z at time t equal to 0 will be equal to a cos k z. I write k is equal to 2 pi by lambda, and this becomes a cos 2 pi by lambda into z. So, I plot this displacement as a function of z. So, I will get a cosine curve. This corresponds to the displacement at t equal to 0. The horizontal axis is the z axis and the displacement is x. This is the actual displacement of each point on the string, and this distance. So, at z is equal to 0, this is 1, and at z is equal to lambda, this becomes a cos 2 pi, which is again 1. So, this distance between two crests or two troughs, that is equal to the wavelength. Now, I write the same equation again, x of z t is equal to a cos, I can use equally well the sine function, or I can use add a phase term here, it does not make any difference. So, at z is equal to 0, the displacement will be as a function of time will be given by a cos of omega t. I write omega as equal to 2 pi nu. So, then this becomes a cos 2 pi nu t, and if I plot this as a function of time, now as a function of time, then I will get a curve like this. This is how the displacement of a point will vary with time, and it will come back after a time equal to t equal to 1 over nu, then this becomes cos 2 pi. So, this is known as the time period. So, this equation represents a wave propagating in the z direction. So, as I mentioned just now, that this is the equation representing the displacement of each point on the string, and I can take the k outside, then this becomes z minus v t, where v is equal to omega by k. Please see, I have taken k outside. So, this becomes z minus omega by k into t. I have replaced omega by k by v. So, I get an expression like this. So, that at t equal to 0, as I had mentioned a few minutes back, the displacement will be, this term will be 0. So, it is cos k z, and at a slightly later time it will be a cos k z minus v delta t. So, the solid curve here, the vertical line is the displacement of the string, and the horizontal line is the z axis, and the solid line represents the displacement at t equal to 0, and the dashed line represents at a slightly later time. So, the whole disturbance has moved through a distance, the whole disturbance has moved through a distance v delta t in a time delta t. So, that v, which is defined to be equal to omega by k, represents the velocity of propagation of the wave. I repeat this, that this is the displacement at t equal to 0. At a slightly later time at t equal to delta t, the displacement is given by z minus v delta t. So, if I plot the displacement at t equal to delta t, then the whole curve gets shifted by a distance v delta t. And so, therefore, in time delta t, it has shifted through, the displacement has shifted through a distance v delta t, and so therefore, v, which is defined to be equal to omega by k, represents the velocity of the wave. And similarly, this distance lambda, as I had mentioned a few minutes earlier, is equal to 2 pi by lambda. The parameter k is known as the wave number. So, here is an animation which I have got through the internet, and I will give you the reference just now. And you see, I am trying to generate a transverse wave on the string, on a string, and this end of the string is made to move up and down in an oscillatory motion, and the wave is propagating in the z direction, which in this case is in this direction. Notice, the frequency is 1 hertz, that is, it goes up and down 1 cycle per second. So, the time period is 1 second. So, let me show this in slow motion, that each point is moving up and down. As you can see from the green bead here, it is moving up and down, and this motion transfers the energy from one point to the other, and the wave propagates in this direction. So, this distance between two consecutive maxima is known as wavelength, and the number of oscillation that it makes per second is known as the frequency. So, I will show this, that once again, that each point on the string makes an up and down motion in a harmonic motion. That is, y, the displacement, let us suppose, is in the x direction, and the whole string always lies in the xz plane. So, it is also known as a plane polarized wave, and since the displacement, the vertical axis is the x axis and the horizontal axis is the z axis, the displacement is always along the x direction. So, it is also known as an x polarized wave. So, let me go back to my slides. So, this is an x polarized wave in which the displacement is a cos kz minus omega t. Each point on the string moves up and down in an oscillatory fashion, as I had shown you earlier. So, then we calculated the displacement at time t equal to 0 and t equal to delta t, and defined the wavelength and also the concept of the velocity of the wave. In order to get this website, I would advise all students to operate this himself. You make a Google search for wave on a string and you will get a website by this. You click on that and you will get the animation that I had shown you. That animation is very easy, will make it much easier for you to understand the concept of wave motion on a string. As I said earlier, that this is the displacement of a particular point on the string. Let us suppose that x is equal to 0 as a function of time. The horizontal axis is the time and the vertical axis is the displacement. So, each point, as I had told you, that each point on the string makes a movement in this fashion. So, the displacement is something like a cos omega t, or you can write it as a cos omega t minus phi, and that is how this is an oscillatory periodic motion. You can also move the string in a circle. So, if I move the end of the string on a circle, then each point on the string moves on the circumference of a circle, and you create what is known as a circularly polarized wave. And in this case, since each point is rotating in a clockwise direction, as the wave is propagating outwards from me, this is known as a right circularly polarized wave. If I rotate it in the anti-clockwise direction, then you will create what is known as a left circularly polarized wave. So, in a circularly polarized wave, the displacement of each point of the string is along the circumference of the circle, and mathematically I can obtain this by superposing two waves, x of z t and y of z t with a phase difference of pi by 2. If I do that, then you will have A cos kz minus omega t, and y of the y component of the displacement is A sin kz minus omega t. If I square and add, I will get x square plus y square is equal to A square. Now, we consider two harmonic motions that are generated on the surface of water. So, S1 is a point source, S2 is another point source. Let us suppose we have two needles. Let us suppose we have two needles on the calm pool of water, and each needle is vibrating up and down in phase. So, each sends out a wave, and these two waves interfere with each other. Now, what is interference? That let us suppose one wave would have produced a displacement like this, and the other wave produces a displacement just the opposite of that. Then the two waves will interfere destructively to produce 0 amplitude. On the other hand, if one wave produces a displacement like this, the other wave also produces a displacement in phase, then the resultant will be the sum of the two, because of what is known as the principle of superposition, that if there is more than one wave, then the resultant displacement is the vector sum of the displacements produced by each wave source, and this leads to the phenomenon of interference, and it is a characteristic of the wave. So, if light is a wave, then it must demonstrate, it must show interference fringes. This is an animation that shows the phenomenon of interference between two waves generated on the surface of water. So, the phenomenon of interference is based on the superposition principle, according to which the resultant displacement at a particular point produced by a number of waves is the vector sum of the displacements produced by each one of the disturbance. So, let us suppose I have two point sources, and the source S1, if the source S2 was not present, the displacement y is the vertical component here, produces a displacement given by omega t minus phi 1, where phi 1 is 2 pi by lambda S1 p, and displacement at p produced by the source S2 is given by A cos omega t minus phi 2, where phi 2 is, as I told you earlier, is 2 pi by lambda times the distance S2 p. So, we are assuming that S1 p and the distance between S1 and S2 is so small that the amplitude produced by S1 and S2 at this point is the same. We are assuming same value of A. So, if both waves are present, then the resultant displacement will be y1 plus y2. So, which I have to sum these two cos terms, and if I sum this, I will get another harmonic wave, another harmonic displacement with this. So, you will get where the amplitude A becomes 2A cos gamma, where gamma is equal to phi 1 minus phi 2 is equal to pi by lambda S2 p minus S1 p. Please see that if S2 p minus S1 p is equal to say lambda by 2, then this quantity gamma becomes pi by 2 and A becomes 0. And if this quantity gamma becomes a multiple of pi, then A square becomes 4A square. So, the intensity pattern, which is square proportional to the square of the amplitude, resultant amplitude, has a cos square gamma factor. So, whenever gamma is a multiple of pi by 2 or 5 pi by 2 or 7 pi by 2, then this will be 0, and when gamma is equal to 0, pi, 2 pi, etc., then this becomes intensity. So, this leads to a variation of intensity, and this is a characteristic of any wave phenomenon. So, here there is the actual interference pattern produced by two thin rods vibrating at 2 points on a ripple tank, on a water tank, and it produces the interference pattern. Although the wave theory of light was first put forward in the 17th century, it was only in 1801 that Thomas Young carried out a beautiful interference experiment. This is a double hole interference experiment. He allowed the sunlight to pass through a filter and then on two pinholes, and the pinholes, the waves emanating from the pinholes interfered to produce dark and bright fringes. So, he could say that light plus light produced darkness, and this could be possible only if light was a wave phenomenon. So, this is the original layout of Thomas Young's experiment. You have two pinholes there, and you have approximately straight line interference fringes that occur here. The bright spot corresponds to the waves arriving in phase, and the dark fringes correspond to the waves arriving out of phase. Thomas Young's interference experiment is considered to be one of the 10 most beautiful experiments in physics. And if I measure the distance between two consecutive fringes, so if the waves appear in phase, arrive in phase, you have a bright fringe. If the waves arrive out of phase, then you have a dark fringe, and that is how dark and bright pattern are obtained on the screen. So, if I measure the distance between two consecutive fringes, then that distance is known as the fringe width, and it is usually represented by the symbol beta, and then elementary calculation shows that the wavelength of light is equal to the beta times the distance between the two pinholes divided by the distance between this screen and this screen. So, if I am able to measure the fringe width, the distance between two consecutive fringes, and if I can measure the value of d and determine the value of capital D, I can determine the value of wavelength. And Thomas Young found that the wavelength of the yellow region of light was about half of a micron, and since the wavelength of light is so small, interference experiments are usually slightly difficult to perform. So, these are the computer generated interference pattern, and they are straight line fringes. If you look at them closely, then they are actually hyperbole, because the locus of the points for S2p minus S1p is a constant, is a hyperbola. But if you look at a small portion of the interference fringes, then they are straight line fringes, and the distance between two bright consecutive bright or consecutive dark fringe is known as the fringe width, using which you can determine the wavelength of light. I am now quoting Denis Gabor that the wave nature of light was demonstrated convincingly for the first time in 1801 by Thomas Young by a wonderfully simple experiment. He let a ray of sunlight into a dark room, placed a dark screen in front of it, pierced with two small pinholes, and beyond this, at some distance, a white screen. He then saw two darkish lines at both sides of a bright line, which gave him sufficient encouragement to repeat the experiment, this time with spirit flame as light source with a little salt in it to produce the bright yellow sodium light. If you have a flame and you put a little salt in it, you get very bright sodium color light. Sodium light is yellow in color. This time he saw a number of dark lines regularly spaced. And read the next line. The first clear proof that light added to light can produce darkness. This phenomenon is called interference and is a consequence of the wave nature of light. Thomas Young had expected it because he believed in the wave theory of light. Denis Gabor, who discovered holography, said all this in his Nobel lecture in December 1971. So then, during the first 10-15 years of the 19th century, there were a large number of experiments which demonstrated that light was indeed a wave, although diffraction experiments were little difficult to perform. The question was, how could it propagate through vacuum? Because a wave requires a medium. For example, as you all know, sound waves, if there is no air between you and me, you will not be able to hear me, because sound waves require a medium. Any wave, people thought, would require a medium, and light propagates through empty space. There is between the sun and the earth, there is very little, there is empty space, and sunlight reaches the earth, shows that light can propagate through vacuum. So, if light was indeed a wave, how could it propagate through vacuum? And the answer came in the middle of the 19th century, around the middle of the 19th century, by James Clerk Maxwell, which established the electromagnetic nature of light waves, that we will discuss in the next lecture. Thank you.